Hey guys, welcome back to the channel. If it's your first time here, my name is Aiden Potts, and we go through math and physics tutorials, as well as how to improve the mindset and the learning skills of a student. In this video, we're going to be going over the graphs of trigonometric functions and how they're derived from the unit circle. We'll go into the transformations of trigonometric functions, and we'll give you a comprehensive strategy on how to graph any trigonometric function. By the end of this video, you'll understand how the sine, cos, and tan graph are defined, as well as the transformations of each of these functions and what they do, and how to graph any trigonometric function. If you find this video helpful, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. So before we talk about the trigonometric functions like the sine, cos, and tan graphs, what we first need to understand is this unit circle, because that's where these functions derive from. So here we have this unit circle, and again this unit circle has a radius of 1. So this radius right here, radius of 1, that's very important. It can also be expressed as the hypotenuse of a triangle. And once we have the hypotenuse of a triangle, we can now express the side lengths B and A based on this angle. So this AB point right here, so A is in the x direction and B is in the y direction, can also be expressed as cos of theta, comma, sine of theta. And if that's confusing in any way, I do have another video where I go through this derivation a little bit more explicitly or more clearly. So if this point can be expressed as cos theta, sine theta, I can say that cos theta is responsible for the x direction or horizontal direction. And sine of theta can represent the y direction, which is also known as the vertical direction. So now that we have the background of the unit circle, we can kind of move forward into the actual sine graph. So again, the unit circle has a radius of 1, and that also is the hypotenuse of 1. And sine of theta is the vertical direction, or the y value. So I've kind of color-coded this unit circle where we're first going to look at the green line, and that's going to be like point number 1 on our sine graph. So at point number 1, you can see that the angle would actually be 0 degrees because it hasn't rotated whatsoever around the origin. So the angle is 0 degrees, and if we have this theta here, that's where we're marking the angle. So right now, since sine theta represents the vertical direction, this green point here, this green line, there actually is no vertical direction here. There's no triangle, like in this example, to show that this would be the vertical direction of B, let's say. So we don't have that because this green line is actually a horizontal line here. So that means that the first point, well, it's at 0 for theta, and it's at 0 for y. So that is point number 1. Now if we go to point number 2 and look at this yellow line, what we did here is we rotated an angle up to that yellow line. So now this arm has gone from the horizontal axis, or the x-axis, all the way to the vertical axis. And that angle is 90 degrees because they're perpendicular lines. And 90 degrees in radians can be expressed as pi over 2. If that's a little confusing, I also have another video that I'll link below as well to show you kind of the derivation or the difference between radians and degrees and how to convert between them. So for this point here, we've now rotated pi over 2. So that is our theta. So I'm just going to write pi over 2. We don't know where our point is yet, but we know it's going to be at an x point of pi over 2. So now I'm going to look at this yellow line, and I realize that it's fully in the vertical direction. And for sine theta, we want it to be in the vertical. Like that is what sine theta is. It's the vertical direction, or the y value. So here, this point, since it's a unit circle, is going to be at 1. Like the y value would be 1. I'll say 1 equals y value. So what that means is our second point is going to occur at pi over 2, and it's going to be at 1. And so this blue line here, it's actually representing the max, and then this other blue line here is actually representing the minimum. So this is the maximum the sine function reaches, is at 1. So I can say equal to 1, and then equal to negative 1. And so that's our second point, the yellow line, is at pi over 2 comma 1. Now for our third point, if we rotate from this axis all the way to this line, we know that that would be 180 degrees, or pi, or actually just pi. So we can write down pi is here, and that's going to be our next point, or our x point of our next point. So at 3 though, it's a horizontal line again. It's very similar to point number 1. So what's actually going to happen is there's no vertical direction for a horizontal line. So again, this point 3 is going to occur at 0. So it's going to be pi comma 0. Now we can look at our fourth point. And our fourth point is going to be if we rotate an angle all the way around here. So if the orange line was rotated 180 degrees and the blue line is just 90 degrees past that, we know that our blue line has rotated a total of 270 degrees. In this case, in radians, it would be 3 pi over 2. And in this situation, again, if we look at this line, it's a vertical line that's going straight down in the negative direction. And we're looking for the point that that line touches. And that will be -1. So we can put our point here on our minimum axis, or axes of -1 here. So now we have 1, 2, 3, and 4 points on our sine graph. So now we're moving on to our last point, or point number 5. And it's actually the same point as number 1, but I want to show you it from going in a full revolution. So point number 5 is all the way around this circle. And it actually ends up being point number 1. That's why I did the similar green colors here. So this full revolution would actually be 360 degrees. In radians, that would be 2 pi. So now we have to figure out what point is at 2 pi if we rotate the entire way around the circle, which would be 2 pi. So it's actually the same as point number 1, so it's going to be 0 again. So I'm going to do, in this green, I'll put our final point, point number 5, and you'll see that that actually now represents the same point as this green circle over here, or this green dot. So now that I have all these points, what I can do is I can connect this graph to all these points. So I can connect this function to pass through all of these points. And we know that the sine graph is going to be a periodic function. So as you can see, 2 pi represents its period because it's now starting again. If we were to continue this, it would go up like that and hit this point here. Very similar to this part of the graph. So this represents a full cycle of the sine graph. And what we need to know is we had some special points we found. So at point number 1, which is the green point, we had it at, well, it's going to be 0 degrees or 0 pi or 0 radians because it hadn't rotated through an angle yet. And it's also going to be 0, 0 because there's no vertical direction on that horizontal line. For point number 2, it rotated pi over 2, 90 degrees to the left or counterclockwise, and we got a y value of 1. Point number 3 was pi and 0. Point number 4 was 3 pi over 2, and this one time it's -1 because it was in the negative direction of y. And 5 would be 2 pi, and then it would be 0, again because point 5 and point 1 have the same y value. It's just representing a full period. Okay, so now that we've done sine, we can now do the graph of cos of x, or cos of theta. So it's going to be the same process, but we just have to remember the properties of cos theta versus sine theta. So cos theta, based on our unit circle derivation, represents the horizontal direction, or the x direction. So here, if we look at point number 1, we see that the angle hasn't rotated, just like normal. The angles are all going to be the same, like kind of the x values of each of these graphs. But what is different is the cos graph is representing the horizontal direction. So this green line here is actually fully in the horizontal direction. There's no vertical component now. So now the cos graph is actually going to start at a y value of 1. It's going to be at 0, this angle 0 radians, but it's going to start at 1 due to it being the horizontal direction. Now if we rotate to point number 2 to pi over 2 like that, it's going to be a 90-degree angle, so we can write it like that. That's actually fully in the vertical direction. So now for cos, it's actually not going to have a value there because cos only represents the horizontal direction. So now I can plot this yellow point, or point number 2, at 0, and that is at pi over 2. For point number 3, we're going to do a rotation of 180 degrees, or pi. So I'm going to put pi down here. And again, this is in the horizontal direction only, so there's no vertical component, but it's in the negative horizontal direction. So we're going to have -1, so we'll put a point right here at -1. For point number 4, we have this rotation of 270 degrees, or 3 pi over 2. And now, again, this is in the vertical direction. So just like the yellow line, this point here is actually going to represent a 0 because cos of theta, or cos of x, only corresponds to the horizontal direction. Finally, if we look at point number 5, we're going to see that it's actually going to go exactly to where point number 1 is. It's just going to represent the completion of a full revolution, or a full period of this cycle. So now I can draw this graph, and I can start from this top here, this top green point, go through the yellow point, bounce off the orange point because it's a minimum, go up through the blue point, and hit the green point. So again, if I were to continue this line, it would go down like that through this other point and keep going. So now we can talk about our special points here for the cos graph. So here, at 0 radians, it's actually going to be at 1. So 0, 1. Then at point 2 is going to be, well, that's going to be at pi over 2, so a 90-degree angle. And that actually went through the vertical direction, so it's going to be 0 because of cos represents the horizontal direction. Then we're going to have pi, because of rotation of 180 degrees, that's going to be -1. For point 4, we're going to have 3 pi over 2. And again, that's a vertical line, so that's going to be 0 for cos. And finally, we have 2 pi, and it's going to go right back to point number 1, which is at a y value of 1. And that would be the cos graph. So now we can talk about the tan graph. And the tan graph, what we need to remember is that tan of theta is equal to sine theta over cos theta. So now it's basically saying that the vertical direction divided by the horizontal direction. So for this one, it's a little interesting, and it's not that much more difficult, but we definitely need to do sine and cos first. So if we look at these special points, we're still going to have like 0 in the x-axis, pi over 2, and pi, then 3 pi over 2, and then 2 pi. And now we have to think about the y value for this. So for the tan graph, if I go to a value of pi over 2, so I go here to this point here, what I'm going to see is there's no horizontal direction. And if it's the vertical direction, so that would be 1 at this point, divided by the horizontal direction, which would be 0. Well, 1 divided by 0, if you look at remember our reciprocal functions and our rational functions, anything there's a 0 in the bottom, it actually creates an asymptote. So here we're going to have I'll do it in a different color, I'll do it in green. I'll do it in green, so this is an asymptote at pi over 2. And the reason is because once we get to that pi over 2 rotation, we see that there's going to be no horizontal direction. So now it's going to be divided by 0. So it's going to get very close to but never touch that because at that point it's undefined. So I'm actually going to draw all the asymptotes here. So if we look at the vertical line, that means that there's no horizontal component of it. So we can look at number 4, point number 4, and that's also a vertical line again. So there's going to be no horizontal component. For the tan graph, it's vertical, which is sine, divided by horizontal, which is cos. So when cos is equal to 0, there's going to be an asymptote. So there's going to be another asymptote at 3 pi over 2 that goes through this. So now we have those two asymptotes on the graph, and we know that a function that has an asymptote is going to get very close to but never touch that value because it's undefined there. So what we can say is, let's look at where our values are 0. So if we look at point number 1, well, that actually does have a horizontal component. In our previous cos graph, we saw that the position number 1 had a value of 1. So it's going to be 0 because there's no vertical direction. Again, sine is vertical. And then divided by 1. So it's defined, but it's just 0. So we can say that there's a point here at 0. So at 0, 0. Next, we can also look at pi. So again, if we rotate fully to the orange position, which would be a rotation of pi, we can see that there is no horizontal, or there is no vertical direction. So it's going to be 0 on top divided by, well, that number actually is defined at 1. So again, it's going to be 0 here. So now we can draw the tan graph by going through this point and close to, but never touching, this pi over 2 line, this asymptote. And then for this part of the graph, it's going to look like this, and go through here, and go up. So again, these two arrow points are never going to touch these green lines, but they're going to come very, very close. And lastly, I didn't do this, so I got to put this last point in. So again, there's a periodic function here that's repeating every 2 pi. So if we were to keep going up, that would be the same part as 0, and again 0 and 2 pi, therefore the period being a 2 pi period. Okay, so now I want to talk about the transformations of these functions. And what you'll see is that the transformations are always going to be the same regardless if they're applied to rational functions, reciprocal functions, quadratics, anything like that. Now we're just applying it to trigonometric functions or periodic functions. So what we're going to have is this similar form, and I wrote it over here to show it a bit more clearly. But we have plus or minus a, the function, plus or minus k, times x minus d plus c. So all those variables represent numbers in certain functions, and they're going to do different things. They're going to transform the function in different ways. So here we have a, which is a vertical stretch or compression. It's also known as the amplitude for trigonometric functions. So if a question ever says that, just know that that's what it means, amplitude. We also have the plus or minus part, which is going to be a reflection. So this first reflection, this green part here, that represents a reflection over the x-axis. And then the other reflection, if there is a negative and there is a reflection, then it's going to be a reflection over the y-axis. So here, this k value, the next one we have is this k value, which is a horizontal compression. This horizontal compression could be known as like the periodic term, because the period is known as equal to 2 pi over k. And so when k was 1, in our last example, the period was just 2 pi, because 2 pi divided by k, which is 1, is just going to be 2 pi. Additionally, I didn't go over this, but the amplitude of the a term in the last example, where it was y equals sine of x or y equals cos of x, was always 1 as well. And the reason we know that is because it went from 0 all the way to a maximum of 1, and then to 0, and then to a minimum of -1. So that difference between where it's starting, or the axis of symmetry, represents the amplitude. And we'll go over that. It might be a bit more clear when we go through a problem. Next, we have the horizontal translation, and this is also known as the phase shift. So if it is minus d, and the d value is positive, that's going to be minus d, because it's going to stay consistent, and that's going to be shifting the graph to the right. If it's plus d, that would mean that the d value would actually be negative, because it's going to be a negative minus a negative, which is a positive, and it's going to be going to the left. Finally, we have the vertical translation, and that's basically just shifting the entire graph up or down, which is very similar to what we've been doing in the previous kind of rational functions. Any other function has the same metric. Okay, so now I'm going to go over the strategy of how to graph a trigonometric function, and this will be the one that you should use every single time, because honestly, once you've done a couple of these, it's kind of a rinse and repeat situation. So don't worry if this looks a little overwhelming. Right now we have a bunch of text, so don't worry, but we'll go through it and it'll be a lot more clear. I just want to go through kind of the steps, and then we'll go through a couple example problems. So for one, it says determine the axis of symmetry. So this is the c value, and axis of symmetry is kind of how it sounds, but where the function is symmetric. What line is the function symmetric on? So we have to determine that, and we have to graph that, so we'll just put that line down. Next, we do determine the amplitude. So graph the min and the max lines, and just put them on the graph without any points yet. Finally, next we do 3, which is determine the period, and like I said before, the period is equal to 2 pi divided by the k value. Next, I think this is something that doesn't really get talked about, but I think it's very helpful. So determine the x scale, which are also special points. So the x scale is actually the period divided by 4. In the previous examples, we kind of did that x scale where we found the point at 0 as a rotation of 0 degrees, and then we did a rotation of pi over 2, and that was kind of 1 point, then the next point was pi over 2, the next point after that was pi, the next point after that was 3 pi over 2, and then finally 2 pi. So those all represent special points, or it could be known as like x scales. So that's important to know, and I think that really helps people understanding how these functions work. So next we're going to determine the graph type. So that's whether this is a sine, cos, or tan graph. And also notice if there's a reflection. So again, that plus or minus. If it's positive, there's no reflections. If there are some negatives in there in front of like the a and in front of the k, then we know that there's a reflection either over the x-axis or over the y-axis. Once we know the graph type and if there's a reflection, what we'll do is we'll start the graph at the phase shift, so at that d value. And that's, I think, really helpful, because it's kind of hard to visualize this graph. Since it's periodic, it goes on forever, to be like shifting it left or right. But if you just start from where the graph normally starts at its new phase shift, then it's a lot easier to understand and kind of easier to shift over. Okay, so now we have an example problem where we're going to apply kind of the things we've learned here and graph this function that has a bunch of transformations on it. So here we have y is equal to 3 sine of 2 times x minus pi over 6 plus 1. So if we look at our strategy, or kind of remember our strategy, I'm first going to, this actually wasn't in the strategy, but it's a good thing to do. I'm going to write out what each of these terms are. So a is the amplitude, and that's 3. So I'm looking at this part of the function where it's a f times k minus x, or x minus d plus c. So I'm looking at all these variables and seeing what numbers they have to then know what they mean. So a, then we have k, well k is equal to 2 in this case. We have d, that's this pi over 6, so that's the phase shift. And then we have c, which is equal to 1. Okay, so now that we have all these values, we can start kind of graphing right away. What I'm going to do is I'm going to graph the axis of symmetry, and that's this c value. So normally the axis of symmetry, if there's no vertical translation, so there's no up or down movement, what it is just at 0. That's the axis of symmetry. Now we have 1, so the axis of symmetry is going to be, let's call it right there. So that is y is equal to 1, and this is as for axis of symmetry. And the next thing I'm going to do is I'm going to plot my amplitude, or I'll plot my max and min line. So our amplitude is 3, so that means it's going to be 3 above the axis of symmetry, so 3 above 1 is 4. So I can put that down here, and I'm going to say that's the max at y is equal to 4. And then 3 below 1, well, that's going to be -2. So I'm going to put this value here as the min, and that is y is equal to -2. So that's the first step. I really think that's important to just kind of put down the axis of symmetry and the max and min lines, and this becomes a lot more easy. We know that the function is going to be a periodic function, and it's going to have maxes and minimums, so knowing where that is right at the beginning is really helpful. Next, I'm going to figure out what the period is. So the period is 2 pi over k. In this situation, the period, or the k value, is 2. So 2 pi over 2, that means the period is equal to pi. The 2's cancel there. Now, once we have the period, I can actually get the x scale. And the x scale is really just the special points that we're going to be going to, where we know where the function is kind of defined based on the unit circle, based on the vertical and horizontal directions. So the x scale is the period divided by 4. So here the x scale will be equal to pi over 4. Now the next thing we're going to do is we're going to start the function, and we're going to kind of see if there's any reflections. So in this case there's not. There's not a negative in front of this a, there's nothing like that, and there's not a negative in front of this k. So we know this is just going to be a normal sine graph. And the sine graph starts usually at 0, goes to 1, then goes to pi, and that x value of pi is equal to 0 again, and then down to -1 at 3 pi over 2. Now what we're going to do though is we're going to do that same process, but instead of starting at 0, we're actually going to start at pi over 6. So here I'm just going to put a point down of pi over 6, and that is going to be our starting point. So we're going to have a value here. I'll put it in purple to make it clear. There's going to be 1 point right there. Or actually, sorry, it's going to be on this green line because that's our axis of symmetry. So to understand what this x scale is doing, I'm going to draw like a simple sine graph. So this is with a sine graph with no transformations on it. I'll make that a bit bigger. So here I want to show you kind of what the separate parts are. So I'm going to draw a line like this. Actually, I'm just going to draw them like this, make it easier. So there's a line there's a line there at the maximum, a line there at the 0, a line there at minimum, and kind of another line right there. So each of these represents a certain part of the graph. So this is like the ascending part, then it goes to the descending part, then it goes to the further descending part to the minimum, and then finally the fourth part where it goes like that. So having these values is important, and once we've divided it up into pi over 4 in this case, we can now use our starting point of pi over 6, because that's the phase shift, to go to each of these points. So this x scale, this part here, so I'm going to look for this point. I already have this point in this graph, that's the pi over 6. I'm going to look for this graph, or for this point here, this x value. So it's going to be pi over 6 plus pi over 4, because that's the period divided by 4. So we're splitting the graph up into 4 different parts. So now to do fractions like this, I'm going to make it 2 pi over 12 to get a common denominator. This is going to be 3 pi over 12. So I'm going to rewrite, instead of our pi over 6 here, to make it easier, I'm going to write it as 2 pi over 12 to make everything under a common fraction. So we kind of have point number 1 of interest. These are all x values. I'll put x values is equal to 2 pi over 12. And then point number 2 was just the point number 1 plus the pi over 4, or the x scale, so the x value to the next point. So in that case, we were adding pi over 4 over 12, it's going to be 3 pi over 12. So here, it's going to be 5 pi over 12. And then we can do point number 3, and that's going to equal, well, if we went from 2 pi over 12 to 5 pi over 12, let's just add the 3 pi over 12, so the x scaling factor, to point number 2. So that's going to be 8 pi over 12. And finally, we have point number 4. And that will be, since you can kind of see a pattern, it went 3 pi over 12 above. So again, it's going to be 11 pi over 12. So once we have these points, we can kind of see that that's going to represent a full cycle at this point. We're going to see a full period of all the possible values in this graph. So I'm going to put each of these points down on our graph here. I'm going to say this is, let's call that 5 pi over 12. This here is 8 pi over 12. This here is 11 pi over 12. And I could just keep going because, again, it's periodic. This is going to be 14 pi over 12, 17 pi over 12, and goes on forever. So to follow this strategy, we've kind of done all the hard parts now, and now we just have to plot the graph. So the axis of symmetry is where we're going to start, because a sine graph starts at 0 and then goes up. But now that it's been shifted upwards 1, the vertical shift, so now the axis of symmetry is not at 0, it's at 1, we're going to put this point here. So that's the start of this sine graph. Next, we know that sine graphs, they go up to a maximum first, if there's no reflections. So we're going to go up to 5 pi over 12, so that's going to be there. And then we're going to go back down to the 0, which is at 8 pi over 12. And then we're going to go to 11 pi over 12, that's going to be at the minimum. And it's going to go back up to 14 pi over 12. So now, if we were to connect these lines, or these points, sorry, with a function, it's going to be a curved trigonometric function like this. It's going to hit all these points and keep going on forever. So we can keep going like this. And even if you wanted to kind of make it so it starts at 0 pi, or at least goes on till 0 pi, we can just go the opposite way. So instead of increasing by 3 pi over 12, we can decrease by 3 pi over 12. So that's going to be negative pi over 12. Let's call that like somewhere here. So this is going to be negative pi over 12. And that, if this was at a 0, this is over here is going to be at the negative 2 value, or the minimum. So it's going to go like that, come back up, and go on forever. So I can put an arrow here like this. So the question says to graph it for 0 to 2 pi. So now all you would end up doing is, we've gone through 0 because this is at 0, and we need to go till 2 pi. And 2 pi for over 12, or I guess trying to figure out what 2 pi for pi over 12 would be 24 pi over 12. So we need to go until 24 pi over 12 to get that 2 pi period cycle that they're asking for. So that was the sine graph, and that's kind of the process we're going to follow for each of these questions. And if that sounded kind of difficult or it was kind of confusing, don't worry. Like, again, these questions start to become really familiar, and once you've gone through this process a couple times, you'll realize that it's kind of the same thing they ask every single time to graph these functions. But originally, it's kind of a weird concept to think about, so don't be discouraged if you're feeling a little confused at this point. Let's go through the next question. So the next question is a cos graph, and we have y is equal to negative cos 0.5x minus pi over 6 plus 3. So here, I want this to be in our form where we have y is equal to af, and then it's k x minus d plus c. This equation here, this k is attached to this x, and I kind of wanted to be factored out of the x and this d term. So what I'm going to do is y is equal to negative cos, and I'm just going to bring this 0.5x, because this has 2 brackets, whereas this only has 1, so that's something to watch out for. And then we're going to do 0.5 bracket x minus, well, if I take out 0.5 from pi over 6, or divide it out, it's going to be pi over 3. Now it's in a form where I can work with, and I can apply our strategy that we've done in the previous example. So first and foremost, I'm going to write out all of these variables. So a, k, d, and c. So a is actually equal to 1, and this is the magnitude. We'll deal with this negative a little bit later. Then we're going to have k is equal to, well, in this case, 0.5. We have d, the phase shift, is pi over 3. And c is equal to 3. So just like last time, I'm going to first start by plotting our axis of symmetry here. So I'll do it in green, and I'm going to plot, let's call that, I'll do it in this line. We'll say that is at 3. So I'm going to mark it as AS, meaning our axis of symmetry. Next, I'm going to plot our minimum and maximum, and that's determined by this amplitude value here, this A value. So here, we're going to have an amplitude of 1, so it's going to be 1 above the axis of symmetry. So that's going to be like this. And then, I'll make it a bit actually higher up. So this is a max at y is equal to 4, and then it's just going to be, the minimum is just going to be below that, so it's going to be like this. So this minimum will be at y is equal to 2. And the axis of symmetry, I should have said this, is y is equal to 3. So again, really important to just kind of write out the axis of symmetry, graph it out. Now you kind of have a visual picture. You know it's going to hit the max, you know it's going to hit the min, it's going to go through the axis of symmetry, and it just starts you off on the right foot. So now we're going to look at the period. So the period in this case, so period, again, is just like last time, is 2 pi over k. So since our k is 0.5, our period is going to be 4 pi. Now we can do our x scale, and our x scale is equal to period divided by 4, because there's kind of 4 parts for a trigonometric function, and the x scale is going to be equal to pi. Now we're going to look at our phase shift, and this is where we start our function. In this case, it's a negative cos function. I'll remove this so you can see that that's just a negative. It's a reflection over the x-axis. So now I'm going to start at the phase shift of what I know a typical cos graph to look like. So I'm going to put my values right here. So this is going to be pi over 3. And I know that we're going to be starting, well, cos usually starts at 1, but it's flipped over the x-axis. So now it's actually going to start at -1. So I'm going to put this point here, starting at pi over 3, and -1 is the y value. Now what we can do is we can add each of our x scales to know our special points that we're going to be going through. So here we have pi over 3. Our x scale is pi, so we're going to add to pi over 3 by pi. And that will give us a value of, we'll say it's here, and we'll say that's 4 pi over 3. Again, because 3 pi over 3 would just be pi, and I'm just putting in common denominators. So we have 4 pi over 3. Next step would be 7 pi over 3. And I'm going to get rid of this min for now. The next step would be 10 pi over 3 and 13 pi over 3. So now we have our x points that we're going to have as like our special points. They're either going to be maximums, they're either going to be minimums, or they're going to be going through the axis of symmetry. So now a cos graph typically looks something like this. If there's no transformations, it starts at 1 and it goes through like that. Very similar to the cos or the sine graph, just a different starting point. So what we're going to do is at pi over 3, this is our first point, so it's flipped. So now we know that this is the minimum point it's starting at. Instead of starting at this maximum, it's starting at a minimum. Our next point is going to be going through the axis of symmetry, so it's actually going to be right here, 4 pi over 3. Next, it's going to go up to the maximum at 7 pi over 3, and then back down to the axis of symmetry at 10 pi over 3. And finally, it'll go to a minimum again at 13 pi over 3. Now, if we connect these values, it's going to be a very long, like stretched out cos graph. And here we have now drawn this graph. If we want to go back like one phase or one x scale, we could do, well, we went up by 3 pi, so we're going to go down by 3 pi in this way, in this direction. So it's going to be somewhere over here, let's call it -2 pi over 3. And that's going to be a point probably around there, because this obviously getting a little messy, but we basically have this x-axis going along that way. I'll make that a straight line. And we're going to start here at -2 pi over 3. And this green line obviously continues as well. So we're going to go through this point here and connect this purple line. Thank you for taking the time to watch this video. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help in math and physics, as well as improve the mindset and learning skills of a student. If you have a certain topic you want me to cover, let me know in the comments down below. Thanks again, and I'll see you guys in the next video.